Dear students, so now we are moving directly into the third module. So we have seen the different topics, those are needed from the last two modules. That is module 1 and module 2, the concept of strain energy, calculation of strain energy, unit load method. So these are the basic things that we require here. So now we are going to talk about indeterminate structures. So what is indeterminacy? Those things has been discussed in detail. So we are going to start with the very basic indeterminate structure, that is the propped cantilever. Okay, it is a very basic indeterminate structure we all civil engineers will first be introduced to. So what is a propped cantilever? So this particular arrangement, we know this as cantilever. Say if I'm giving a prop or a support at this end, now this particular structure is called as a propped cantilever. So if you are trying to convert this into a beam with forces rather than the support conditions, this can be represented as a beam with a force or a prop. If I'm marking the support reactions, I'm going to get a beam. So a fixed end can have support reactions like this, and the roller will be having another support reaction like this. So this is the representation of a propped cantilever. We have the basic equation to calculate the degree of static indeterminacy for a beam, that is ds is given by number of reactions. Okay, let's get familiarized with this particular equation. So what we have is the degree of static indeterminacy, which is calculated using two parameters. One is R, which is the number of reactions that are unknown. Okay, if we have some value, then they are not unknown. So unknowns. And what we require is the number of equilibrium equations. Okay, that can be, I don't know what is the naming convention that you have used in the previous modules. So basically, if you are considering here, I'm using this variable e for that, which basically talks about number of equilibrium equations. And when we speak about equilibrium equations for a 2D frame, okay, 2D frame or 2D beams, we have three: sigma fx equal to 0, sigma fy equal to 0, and sigma m equal to 0 for any 2D beams or frames. Okay, so we have three equations. Now we are going to get the equation. So ds is equal to R, the number of unknown reactions, minus E. That is a basic equation, and you should be familiar with more complicated type of indeterminacy like internal, external. So we are basically talking about the very basic concept, that is external indeterminacy, which is R minus E, where R is the number of reactions and E is the number of equations of equilibrium available. So in this particular beam, we can see that we have reactions, say reaction 1, 2, 3, and we have one more reaction due to this roller. So we have 4 reactions. So for this propped cantilever, R is equal to 4. And how many equations do we have? It's a 2D beam, so we are having 3 equations of equilibrium. So E is equal to 3. When we substitute it here, we will be getting 4 minus 3, which is 1. So this propped cantilever is a structure which is having degree of static indeterminacy as 1. Okay, if you are considering any determinate structure, for example a simply supported beam, that's a very first beam that you got introduced to, a simply supported beam. If you are converting this into forces, we'll be having 2 reactions for a hinge and 1 reaction for roller. So you can find we have 1, 2 and 3 equations. Degree of static indeterminacy D is equal to R minus E. The number of unknown reactions are 3. Equations of equilibrium what we have is a it's also 3, so it's going to be 3 minus 3, which is 0, and a structure which is having ds value as 0 is called as a determinate structure. So we know that to analyze a determinate structure, we just require these three equations. Okay, this is basically like simultaneous equations. We know that if we have a system of equations like x plus y equal to 2, x minus y is equal to 3, some equations if we are having, we know that here there are two unknowns and two equations. So this system is determinate. That is, the number of unknowns and number of equations, okay, are same. So it is determinate. But if you are given an equation like this, x plus y plus z equal to 3, x minus y equal to 2. Okay, so now what the case is that we have two equations, but there are three unknowns. Okay, we know that solving this is not possible. This is indeterminate. Okay, whenever the number of unknowns is more than the number of equations, the structure or the system, we call it as indeterminate. Similar is the case here. So if you are trying this particular beam, which is propped cantilever, there are 4 unknown reactions and 3 equations. So it is indeterminate. But if you are considering a simply supported beam, 3 reactions, 3 equations, it is determinate. And there is another case that can come. For example, if we have system of equations like this, x minus 2y equal to 4, x plus 3y is equal to 8. Now what is the case here? Here you can see how many unknowns? Unknowns are 2, x and y. So we can basically like the number of unknowns are 2. And how many equations do we have? We have 3 equations. So what is r minus e? R minus e is minus 1. What is this situation? If we are trying to solve this, we are not going to get a unique solution, because when you consider these two equations, you will be getting one value of x and y. When you consider these two, you are going to get another value of x and y. And when we consider these two, okay, this and this, we are going to get another set of solution. So here there is no unique solution for this problem. So this system also, we call it as a deficient system or an unstable system. Okay, so when you are dealing with truss, you will be learning this. You might have learned this in detail. What is indeterminate, what is determinate, and what is deficient. So 3 types of trusses you might have already got introduced to. So this is the basic concept. When the number of unknowns is equal to number of equations, it is determinate. When number of unknowns are more than number of equations, it is indeterminate. Whenever the number of unknowns are less than the number of equations, it is called as a deficient case. Okay, so that is the basics about indeterminacy and how to calculate the value. So we have seen the simplest and basic indeterminate beam, which is the propped cantilever. So we know that the number of unknowns are 4, number of equations are 3. I need one more additional equation to solve this. That's what this particular number or ds deposits. Okay, that is, if we are getting 1, which means that an additional equation other than the equation of equilibrium is required to solve this. Okay, so now we are going to the part 1. So in part 1 we are dealing with the strain energy method of solution. So let's directly jump into that. So to understand that, we need to have a theorem that we already learned in module 2, which is called as Theorem of Least Work. Okay, Theorem of Least Work. This theorem you learned soon after you learned the Castigliano's equations. Okay, this theorem is actually Castigliano's equations of Castigliano's theorem of least work, but generally called as theorem of least work. Fine. So you have learned it in module 2, but still we are just refreshing what it is. So if you want to define this particular theorem, so the easiest definition what is available is, I will write it down. The redundant reaction, okay, the redundant reaction components of a statically indeterminate. Okay, the term is very important. The redundant reaction components of a statically indeterminate structure are such as to make the internal work. Okay, what is internal work? Another name for internal work. When I'm stretching a rubber band, I'm doing some work done and it is getting stored inside the material as strain energy. So another name for internal work can be strain energy, a minimum. Okay, so this is the theorem statement. So it says that the redundant reaction components of a statically indeterminate structure are such as to make the internal work or strain energy a minimum. Okay, that's a theorem statement. What does this mean? Okay, it means very simple concept that when we see an indeterminate structure, just like our propped cantilever, we can, a better way will write the Castigliano's equation so that this concept can be clarified in simpler terms. What is Castigliano's theorems? Castigliano's first theorem says that if strain energy can be represented as a function of forces, dou u by dou p is equal to delta. That is, the partial derivative of strain energy with respect to a force will give the displacement at the point of application of the concerned force. What does this mean? Say if I have a beam, I'm considering a cantilever beam, a determinate structure. Fine. And if I can calculate the strain energy, okay, assume that there is some kind of loading, say here on load, here a lot of loading is there, some UDL is there, a moment is there, a complicated system. So in this particular system, if I want to calculate the vertical deflection at any point, say at this particular point, I want to calculate the vertical deflection. I'm naming it as B. Okay. So Castigliano's theorem says that if I want to get a displacement at this point, okay, assume there is a load P at this particular point B. Now the deflection at B, that is delta B, or we normally call deflection as Y. So YB is equal to dou U, which is the strain energy of this beam, by dou P. Okay, this is the Castigliano's first theorem. Okay, and again consider this point as C and the load is P1. Fine. So if I want YC, what I need to do is dou U by dou P1. Fine. So if I do this, I'll be getting the value of YC. If I partially differentiate the strain energy with P, I will be getting YB. If I'm doing it with P1, I'll be getting the value YC. Fine. And let this moment be M. Now I will give some name also. Let this point be named as point D. Okay. Then here what I'm considering is a rotational force, and the rotational force causes rotation or slope or theta. So theta D, that is rotation at this point, is equal to dou U by dou M. Okay, in all these cases, U is the strain energy of this beam. Okay, let U be the strain energy. So this is what basically Castigliano's first theorem is. Dou U by dou P will give delta. Okay, this is partial differentiation. Fine. Now we are going to extend this concept to a indeterminate beam. So we will do it on the case we have already considered, which is the propped cantilever case, right? So let there be some loading. Okay, so I can represent this as a system like this, right? As forces, I remove the support conditions and I place the reaction, so I'm getting something like this. And I'm calling some names. Let this be A and this be B. So I'll be having a reaction RA, HA, MA, and this is RB. Fine. Now let U be the strain energy of this given system. Okay, we know how to calculate strain energy. It is given by integral m square dx by 2ei. How to calculate strain energy? We have earlier we have seen that. Okay, so I'll be getting the strain energy. Let U be the strain energy. If U is the strain energy, what will be dou U by dou RB? Okay, what will be dou U by dou RB? We have seen the Castigliano's first theorem, which says that if I do dou U by dou P, I will get the vertical deflection at B. So if I do dou U by dou RB, what will I be getting? I will be getting the vertical deflection at B, right? Because RB is acting at this point. If P was acting here, and when I did dou U by dou P, I got deflection at B. When I did dou U by dou P1, I got deflection at C. When I did dou U by dou M, I got the rotation at D. Similarly, in this case, when I do dou U by dou RB, what I will be getting will be the YB value. Okay, and as this is a roller support, okay, what is going to be the deflected shape of this beam because of the given loading? Can you predict that? Because of this loading, we know that it will deflect something like this. Right? Are you able to appreciate it? For some distance, it will be a straight line and then it will deflect like this. Are you able to appreciate the shape? Okay, so it's more like, so if I have a scale, this end is fixed, which means whenever we are talking about a fixed end, just hold it. Okay, just hold it tightly in your hands. Okay, that is the fixed support. And when we talk about roller, it is basically roller or a hinge is something like this. Okay, just place your finger like this, which will represent a roller support, and this will represent a fixed support. Okay, now if I apply a load, okay, if I apply a load, how will it bend? So you can see that it will be bending in this format. As this is fixed for some moment, so I'm just assuming it as a cantilever for time being. So this is a cantilever, which means only support is here. And now when I apply a force, you can see that for some distance, this portion remains a straight line. Then only it is bending. See here, for some distance there is no deflection, then it starts to bend. And what is that due to? Because we know that for a fixed support, there is no vertical displacement, no horizontal displacement, and no rotation. That's why some portion remains straight and then it starts to bend. But instead of that, if it was a hinge or a roller, which means I'm just placing it at my fingertip, now you can see that if I apply a force, it starts to bend right from this point, right? It starts to bend right from that point, because in case of a hinge, in case of a roller, we know that only restricted is the vertical displacement. So this point remains here itself. It can rotate. That's why the rotation starts from here itself. But if it is fixed, the rotation at the fixed support is 0. That's why for some portion it remains same, remains straight. Now we are going back to this case. So this is a fixed end, just like this case. So for some portion it will be straight line and then it starts to bend. Okay, so for some portion it is straight line, then it bends, okay, because of the loading. And this is a roller, so it starts to bend from the right from that point, but it cannot move vertically. So this is going to be the displaced profile of this beam due to the given loading. Fine. So what is the final deflection at B? The final deflection at B is 0. Okay, and this is what is said in the theorem of least work. Okay, the redundant reaction. What is redundant? Redundant are any reactions that is okay. For example, if I'm considering a cantilever beam, okay, this just like here. So if when I was having a prop at the end, when I remove this, now what happens? It is a cantilever beam which is a determinate structure. On introduction of this reaction, it became indeterminate. So whatever reaction I included to make the structure indeterminate, those are called as the redundant reactions. If I remove this reaction, it becomes cantilever. If I place this reaction, it becomes indeterminate. So this reaction, here it is RB is the redundant. So now you read the statement. The redundant reaction in case RB of a statically indeterminate structure are such as to make the internal work or strain energy a minimum. Okay. You might be familiar with the concept of maxima and minima in mathematics, right? A function will be having a maxima or minima when its differential is equal to 0. That is the same concept that we have used here. So it is said that the structure make the internal work minimum, which means work is the function, u is minimum. To get that, I can do the mathematical operation. A function y is having minimum when dou y by dou x equal to 0. Similarly, if I am differentiating the strain energy, I can equate it to 0. So this particular statement is said as the theorem of least work. When you differentiate the strain energy with respect to a redundant, you can equate it to 0. That's what this theorem of least work is. So now we have seen the concepts of what an indeterminate structure is, what are redundants, and what is theorem of least work. Once you understand these things, we are going to apply this theorem of least work to analyze indeterminate structures. Okay. I don't think everything is clear to you by just viewing this video, but don't worry, we will practice problems which will help you to reinforce all these concepts that we discussed. So along with the problem, we will again and again discuss this theory, so that theory will be reinforced. Along with that, you can easily solve problems. Thank you.